All right, we're live. I can't see if you see that someone has asked a question here and I'm not acknowledging it, let me know because I might not notice it. So it's good to be back. I'm happy to report I didn't get selected for the trial of the century. I didn't actually get selected at all. I just spent 2 days sitting in a room waiting to be called, and I never got called. It's good to be back. And good to be getting on to some interesting stuff in class here. Some really practical stuff that you're going to see over and over in the public health literature, and being able to calculate these things and interpret them is going to be very important to you. Confidence intervals are the primary result that you'll see reported in many publications. And the t-distribution is a very common way of getting confidence intervals and doing hypothesis tests. We're still not getting into hypothesis tests today, but this is really setting up the framework for it, and we'll show you next class that there's actually some equivalency between confidence intervals and hypothesis tests. So at the end of today, you'll be able to start doing hypothesis tests if you had to, using the confidence interval approach. I'm going to start with a review again of sampling distributions because they're key to what we're doing today, and then go straight into confidence intervals and extend that to the t-distribution for confidence intervals. This is a little bit out of order of the way that it's done in the book. They have all about confidence intervals and hypothesis testing in chapter 4. I kind of felt like that is a couple of big concepts to try to introduce in one class. So there's really one main concept in this class, and that's the confidence intervals, and then next class. But we needed a little bit more to talk about, so we also do the t-distribution, which is not really a big conceptual leap like the confidence intervals and hypothesis testing are, and then we'll go on to hypothesis testing next class. So in the last class, or in the last recording anyways, we got into the central limit theorem, which relates the distribution of something we observe in a population to the distribution of its averages in samples. The distribution of individuals in the population, that's what we call the population distribution. So the heights of adults, if you're looking at the distribution of all individual heights, that's a population distribution, whereas a sampling distribution is where we draw samples of a given size. So you take one sample size and draw that over and over. So maybe we take n equals 10 adults, draw 10 adults, calculate their average height, and then do that over and over and get the average heights of samples of adults of size 10 adults. That's the sampling distribution. So the sampling distribution is something that you don't observe directly. Typically, you only observe one sample, but that distribution of what you would observe in the samples is the basis for confidence intervals and hypothesis testing. So you have to be able to think conceptually about what the confidence intervals hypothesis tests mean in terms of the sampling distribution, which is why we spent a whole class talking about the central limit theorem, and I'm going to review it a bit more today. So, well, the example we have on here was the serum cholesterol level of individuals, and that's this broad distribution, and then the mean serum cholesterol of samples of size 25 looks something much taller and skinnier. So the central limit theorem told us that the mean of these two distributions is the same, that the standard error of the sampling distribution was equal to the standard deviation divided by square root of n, and that for large enough n, the sampling distribution will always be normal. Those are the three parts of the central limit theorem. So once again, the first part of the central limit theorem is that the population distribution and the sampling distribution have the same mean. The second part was this relationship between the standard error of the sampling distribution and the standard deviation of the population distribution. The standard error is just a standard deviation. It's just that it relates to, we call it standard error because it relates to the sampling distribution, not to the population distribution. So it's a terminology just to avoid confusion between those two things. And then finally, that for large enough n, say approximately greater than 30, that sampling distribution will be normal no matter what the population distribution is. So as n increases, it affects the standard error. The population distribution is what it is, but the sampling distribution changes as you change the size of the samples. Importantly, the width of it narrows the more n increases. The larger your sample size, the narrower your sampling distribution. And additionally, the more it looks like a normal distribution. Just a second. And I showed you that you could also apply this relationship between population standard deviation and the standard error of the sampling distribution to proportions, just using this equation, square root of p times 1 minus p, instead of just sigma. This is your approximation. The square root of p times 1 minus p is your approximation for the standard deviation of a proportion. So put together with the central limit theorem, given some population distribution, we can calculate what the sampling distribution is, and that is what we're going to use today to calculate confidence intervals. Any questions so far? How do y'all feel about being in class again today as opposed to watching the video from home? Yeah, I like the classroom too. It was kind of boring sitting at home on my couch recording the lecture. It's way more fun with actual people present. Plus, I can tell if I'm like going too fast, or if I need to stop and talk about something more, and it's hard to tell when I'm just sitting on my couch. Okay, I'm glad some of you at least feel the same way as well. I guess you would, or you wouldn't be here. Yeah.
When we should apply the other formula for
So
proportion?
you apply the other formula for proportion when you're dealing with the prevalence of a binary variable. So instead of something like serum cholesterol, you're talking about the proportion of people who have cholesterol greater than 230. That would be an example of a binary variable. Either yes, you have cholesterol above 230, or no, you do not. You draw a sample of size 30, and 15 of them have a cholesterol of greater than 230, then your proportion estimated from that sample is 0.5. Yeah. So that p, it's a fraction. So a point estimate is a single number that represents your best estimate of something you're interested in. and it's your best guess for something that has a true value in the population. It could be, if we were talking about ages and we were interested in the average age of Hunter College students, for example. If you had to just give one number, either based off the top of your head or based on a sample that you took the average of, it would just be one number, like 38, and that is your best guess, but that does not give any indication of your uncertainty in that guess. That's where we get into providing intervals around those estimates. And instead of one number, a confidence interval has a lower and an upper value. Those values are typically going to be centered around your point estimate and go up and down by what is called your margin of error. So instead of just saying we think that the average age is 38, we might give a margin of error of 3 years. So plus or minus 3 years, so between 35 and 41, instead of just that point estimate. So the idea is to formalize the amount of uncertainty that we have around some population parameter like average age. Here's an example. Let's take a random sample of 309 infants. From that sample, we calculate their average birth weight, 119.6 ounces, and a standard deviation of 18.2 ounces. That might either be known from the population, that's going to be one scenario, or estimated from the sample is a slightly different scenario. And we took this sample because we want to estimate the average birth weight of infants in the population. Can someone give me an example of how this might fit into a public health study? Why would you be trying to estimate the average birth weight of some population? Yes?
You might want to compare whether the average birth weight of females born to mothers is lower than the average birth weight of females born to mothers.
So a good example, you might want to say whether there is a difference in the average birth weight compared to between mothers who smoked and mothers who did not smoke. That would be an example of a two-sample hypothesis test if you had observations of mothers who smoked and who did not smoke. In this case, we have only one sample, so we would have to compare to some previously established known value, something that there is no uncertainty in. So if we had a birth weight registry from which we could calculate the average birth weight of all infants born over the same period of time, that would give us an exact calculation of average birth weight in the population. And then you could do this with just one sample. You could calculate your average birth weight of, say, infants born to mothers who smoke, or anything else of infants born to mothers who are under 20, or anything else, and compare that to this reference value. And then, of course, when you draw samples, we know because of the sampling distribution, there's always some randomness in that average. The randomness is going to be smaller here because we have a sample size of 309. It's pretty big, so the variability in the average birth weight of 309 infants isn't going to be very big compared to the variability of individuals. But still, there is some variability. And the question that we're going to be able to answer today is, what is the 95% confidence interval on the average birth weight of this population of infants? So we've got the point estimate, 119.6. We've got a standard deviation of, that's the variability of individuals. We're going to use those pieces of information to provide a confidence interval around the average birth weight in this population based on just one sample. Does that make sense? And that is distinct from this not scenario here. What interval contains the birth weight of 95% of all the infants in the population? Does that seem, that should seem like of course not, like I would never mix that up. You probably will mix it up at some point, and that's okay, but the more you can start distinguishing between those things, the better. It's a, distinguishing between individuals and samples is what that distinction is. The interval containing the birth weight of 95% of infants, that would be found from the population distribution, whereas we're looking for a confidence interval on the average birth weight. You see average, you think sampling distribution. And you'll get tricky questions about this on the test, making sure you understand whether you're thinking about the sampling distribution or the population distribution. Repeat about.
You said this you were saying that something could be found if we were population distribution.
Right, so the interval that contains the birth weight of 95% of all infants in the population, to answer that, you need the population distribution. You would need the mean and the standard deviation, and you could use the z-table, or you could use the empirical rule. You could go plus or minus 2 standard deviations from the population mean to get that interval. But in order to calculate a confidence interval on the average birth weight, that is going to be based on the sampling distribution and the standard error, not the population distribution and the standard deviation. Of course, the means are going to be the same, but the standard error is different from the standard deviation. And the standard error is, what is it compared to the population standard deviation? Yes? Yep, standard deviation over the square root of the sample size. So the standard error is always less than the standard deviation, which makes sense because the average properties of a group of individuals is less variable than the individuals themselves. So how do we construct the confidence interval? We're going to start from a sample. That is the data that we collect. When we go into a study and we observe 309 infants, that's a sample. We're going to calculate the mean of the sample data, and that will be our point estimate for the mean in the population. It's the best estimate that we have. Even though we know there's some sampling variability, the best estimate we have is what we calculate from the sample. And then we're going to calculate this margin of error, the uncertainty above and below that sample estimate, using the central limit theorem and the standard error. If we have a large sample size, all you have to do is add and subtract 1.96 times the standard error in order to get a 95% confidence interval. So you calculate that standard error as sigma over square root of n. You calculate your sample mean. You add 1.96 times your standard error to get your upper limit, and subtract 1.96 times your standard error to get your lower limit. And you can use this, the normal distribution or the 1.96, either if sigma is known, so it's not estimated, or, and I'm actually going to change this A part here now that I look at it. This is not quite right. This is your advantage you get for listening to the lecture. This is really only if you have a very large sample, not just n greater than 30. I'm going to say 300. And just put in, call this very. So that the n greater than 30 was good enough for us to assume a normally distributed sampling distribution. But it turns out that actually that if we're estimating S, you underestimate the variability of that distribution a little bit, and that's what we're going to get into in the latter half of class with the t distribution. If you have a very large sample like 300, then it really doesn't matter. Normal distribution is fine. But if you estimate S from a small sample, or at least even not a very large sample, you're going to use the t distribution instead. The t distribution, if you're estimating S, is always safe. I'll show you the table a little bit later. Just it becomes indistinguishable from the normal distribution once you get to very large sample sizes. So here's a couple formulas for you just for calculating the 95% confidence interval, the 99% confidence interval, and in general for other confidence intervals besides 95 or 99. This is under the normal approximation. And so these all involve calculating the standard error, and the way you calculate the standard error is a little bit different depending on whether you have a continuous variable or the proportion of a binary variable. But other than that, your calculation is the same. And I'm going to change this again to 300. A little hard to. I have a slide in here a little bit that'll show you how much of a difference it makes for n equals 30. It's not a huge difference, but it is a difference. How do you interpret these confidence intervals? Let's start with what they're not. It does not imply that 95% of the population values lie between these limits. So if it's a confidence interval on infant weight, it doesn't mean that 95% of infants have a weight within those bounds. Is that, everyone believe me? Yeah, because this is a sampling distribution, not a population distribution. It's a really common misconception about confidence intervals. And it does not account for bias in the point estimate, either due to your sampling procedure or a measurement bias. This is only variability due to sampling. So it means that if you were to draw another sample of the same size, you would get a somewhat different estimate. And that's the kind of variability that confidence intervals account for. What it does do is it provides an interval within which we're 95% confident that the true population mean lies. Or alternatively, if you were to repeat your experiment 20 times, then approximately 19 times, the confidence interval that you calculate would contain the true population mean. So really, if you repeated your experiment many, many times, 95% of the time, your 95% confidence interval should contain your true mean. If we calculated a 99% confidence interval, then 99 times out of 100, you should capture the true mean in that interval. So in all of this, that population mean is assumed to be fixed but unknown. So the population mean itself, it doesn't have error to it. It's just like that is the true average birth weight of all infants. There's no error in that, but we don't know what it is. So what this confidence interval does is represents our uncertainty in what that true value is. That can be a bit of a hard concept to get your mind around. We're estimating something that is a single fixed value. There's no error on it, but it's our knowledge of what it is that has error. This is a so-called frequentist interpretation of confidence intervals, the fact that there is one single true value. If you asked the Bayesian, they would have a different interpretation of it, but this is what I tend to adhere to and what we do in this class. So, and if we took repeated samples and constructed the 95% confidence interval around every one of them, then 19 out of 20 times those intervals would contain that true mean and the other 5% would not. This is just a pictorial representation of that. So this is a simulation where samples are drawn from a normally distributed population of mean mu, and we're drawing repeated samples and calculating a 95% confidence interval from them. And the ones in black cross the correct mean, and the ones in red do not. And you'll see that the size of them changes some because we're estimating the standard error from the sample. So in some samples, you'll get a greater standard deviation, and in some, you'll get less. So they're not all the same size, and they also don't all have the same mean. But 19 times out of 20, this true mean is contained within that interval. That's what's important about the 95% confidence interval. So keep that in mind when you are reading and interpreting about a confidence interval or calculating them yourself, that the exact values that you observe, those are not truth. They're based on a sample. So there's, even if you did your experiment exactly the same way again, but drew a different sample, both your width and the center of your confidence interval would change, which is part of why I don't support reporting too many decimal places in these things, because the decimal places, beyond maybe one decimal place, depending on what your sample size and accuracy is. Certainly reporting a bunch of decimal places on your margin of error doesn't make sense, because it's just not, it's not something that you have that kind of a certainty in. It's subject to sampling variability. It's hard to remember when you just put like a whole bunch of your life into collecting a data set, analyzing it, and all of this, to think that the p-values and the confidence intervals and the point estimates, none of those are like the truth. Like they're just an estimate based on one sample, and if you did it again, you'd get different values. But the thing that we count on, if we do everything correctly, is that 19 times out of 20, this confidence interval will contain the true population mean, even though we can't be sure about the point estimate or the bounds of it. Let's do some Q&A. I'll do the questions, you do the answers. So is a 99% confidence interval larger or smaller than a 95% confidence interval? Put up your hand. Let's see, someone new. Okay. Oh, you haven't put up your hand before. What do you think? It's larger? You want to explain why? That's okay. That's okay. Audrey, you want to try?
Sure. I think it's larger because, well, it's 2.58 times standard error.
That's cheating.
But it's larger because in order to capture more certainty, more values.
Yeah, in order to capture more certainty in what the true population mean is, you need more values within your interval. Does anyone have another explanation? Yep.
Can you go back to the picture with the intervals crossing?
Yeah.
Okay, so for 95% confidence, there are 6 red ones up there. Let's just say there are 5.
Yep.
So for 99%, there would only be 1 red one. So that means the interval has to be wide enough to capture all of
Very good.
more black ones.
Yep. Yeah, so we have like, I don't know, 6 or something red ones that did not capture the true population mean. If you wanted, and so every 5 out of 100 here is not capturing the correct mean. If you want to increase that or take that down to only 1 out of 100, then they need to be bigger, because the center of them isn't going to change just by changing the degree of confidence. Very good. Any other thoughts about that or other ways of looking at it? I'm impressed, because at the beginning of class, I suspect, and if you went out into the general population, most people would get this first question wrong. Like, and I don't want to say why, because I might confuse you again. But you know, 99%, it sounds like you have more confidence. So why is your interval bigger if you have more confidence? It is. So the second question is, the size of a confidence interval increases, does the confidence increase or decrease? This is kind of the same question. As the size of the interval increases, does that mean that the level of confidence increases or decreases? What's that? It increases, right. That's sound a little funky? Yeah.
I mean, you're sure that most of the times, 99 times out of 100, your value, your point value would be
right. Yep. So you could have 2 confidence intervals of different widths if they came from different samples. So if, yeah, I'm saying if our information, our data are fixed, and if we adjust the confidence level or adjust the size of the interval around it, does our confidence in the true mean increase or decrease? This is one that really trips people up, because, you know, if you think about, if you're really confident, then, you know, you should have some really narrow range, right? But the thing is here that the information is fixed. So if you put a small range around it, you can't be very confident in that. But if you put a really big range, you can be very confident that the truth is found in that range. How about this one? As the sample size increases, does the 95% confidence interval increase or decrease? Yeah. It will increase. Why? Decrease. Why is that?
Because when you have a larger sample, you more close to the real value. So most of the value will concentrate.
When you have a larger sample, you get closer to the real value of the mean. Your standard error will.
Yeah.
I think you're on it. Let's hear another answer. Yeah.
So if your n increases, the sample increases, you will instead of going for the false calculating confidence interval, you have to take a specific sample.
Yeah.
So I was like, if we increase the number population or sample size, I think it should not cause much effect.
It will affect it.
But it will be on negative side, decrease.
Yeah. I don't know. Let's, any more? Yeah.
So the standard error is the standard deviation of population over the square root of the sample size, right? So if n increases, the denominator is increasing,
Yep.
so the standard error will decrease. So
That's right.
You're adding, subtracting a smaller amount of your weight estimate when you're creating your confidence interval. So the width of the interval will increase, but then your estimate of the population mean will be better.
Yeah, so here's someone with a very mathematical mind. In terms of the formulas, that's exactly correct. Your standard deviation is, or your standard error is the standard deviation over square root of n. So as n gets larger, standard error gets smaller. And as standard error gets smaller, your margin of error gets smaller. Yes?
I mean, I agree with that on average, but you could have two samples, and even the smaller sample, you just happen by chance to have less variability.
Right.
The larger sample, you have extreme values.
Yeah, so the point is that there is sampling variability in the individuals you draw and the standard deviation that you estimate. And so even for a smaller sample size, you might just happen to draw, say, n equals 4 people who are very similar to each other. And for that sample, you could end up with a smaller estimated confidence interval. And that is true. There can be, if you draw enough samples, you will observe a great deal of variation between those samples. On average, if you draw larger samples, you'll have smaller margins of error and smaller confidence intervals. So, but you're right that for any two particular samples, you can't say in advance what standard error you would estimate from them.
Unless you can ensure that the sample is representative of the population.
Even if your sample is completely representative of the population, you will have sampling error. So we're making that assumption here that this sample is a simple random sample that is representative of the population. But just the fact that you're not observing the whole population, you're observing only a few individuals, you could happen to draw the shortest people in the population on one particular draw, not because of any shortcoming of your sampling method. Even if everyone has the same probability of being sampled, you will still end up with some samples of all short people or some samples of all tall people, or samples with great variability within that sample. That's random sampling error.
If the sample is equal to confidence interval is limited to 0?
Sorry?
If the sample is equal to the population that we are studying.
What do you mean the sample is equal to the population?
We don't have the sample, we have the population.
Okay, we have the population, yeah.
So
Yeah.
the confidence interval is close to 0.
If you have the entire population, then the confidence interval is meaningless. You don't need to put any uncertainty around your point calculation. You know exactly what the population mean is then. Yeah, this is only to represent sampling variability. Good question. One other case where this would be strictly true is if the standard deviation is known from the population, if you're not estimating it from the sample, which is one of the cases where we will use the z distribution. So you're using your point estimate, the average from the sample, but you're using an already known standard deviation. In that case, then standard error and the width of the confidence interval would strictly increase with n. Okay, last one. What does the confidence interval tell us about variability of individuals in the population? If all you have is a confidence interval, what does that tell you about the variabilities of individuals? Let's see. Yeah. Yeah. Basically nothing, yeah. If you knew the sample size, then it would tell you something, but you could get that same standard error from a whole range of combinations of standard deviation and sample size, so it doesn't tell you anything about variability of individuals. Another very common misconception about confidence intervals. All of these Q&As are based on questions I've asked on previous exams that a lot of people got wrong. So I'm not trying to trick you. I'm not going to go through this example, but it's here for you to look at and just to give you an idea of some of the kinds of calculations that I think you should be able to do. There's a link to a mini tutorial that I made here that's on YouTube, and I linked to it also from the lecture post. I did one for using a z distribution and one for a t distribution. So let's get on to this student's t distribution. What we've done so far assumes either that we have a very large sample size, like n greater than 300, or that the standard deviation is known. There's no uncertainty in the standard deviation. So as long as we have something very accurate for sigma, we can use z. Yes, question? Yes, just the standard deviation of the sample. Yeah, we either know sigma because we have it calculated from an entire population, or we estimate standard deviation from the sample, and if it's a very large sample, like greater than 300, then we can assume that it's close enough to the population not to worry about it. As I'll show you, you can, even for large sample sizes, you can still use t. But it's especially important that you use this distribution when you're estimating the standard deviation from a small sample. And it was developed by this guy, William Gossett, who called himself student because he wasn't supposed to be publishing papers as he worked for Guinness. But he was doing quality control for batches of beer and wanting to know if they were systematically varying from properties that were supposed to be fixed for the beer, like alcohol content, and found that when he calculated things like confidence intervals and p-values to try to make a decision about whether something had changed in their manufacturing process, there was too much variability when he used a normal distribution, and figured out that the reason for that was because of this uncertainty in estimating the standard deviation, and developed this t-distribution to deal with it. So given a sample, you're going to calculate the t-statistic in the same way that you calculated the z-score. So it is a property of a sampling distribution. The only difference is that when the population standard deviation is unknown, and you're estimating it S from the sample, we're going to call this a t-statistic. And I'll show you that the distribution of values that you estimate in this way is a little bit different than the distribution of z-scores that you estimate as we have before. So when we don't know sigma, the usual case, we estimate the standard deviation of individuals from a sample. The standard error is not going to be sigma over square root of n, it's going to be s over the square root of n. And the reason that matters is that it turns out that the thing that looks like the z-score is not actually normally distributed. It is t-distributed. So we're going to assume that we're drawing individuals from a normally distributed population with mean mu and standard deviation sigma. Then this one sample t-statistic is just, for the sample, the mean of the sample minus the known or the hypothesized population mean divided by the standard error estimated from the sample. And this is, for small samples or for any sample size, it's t-distributed with n-1 degrees of freedom. And I'll tell you how to calculate degrees of freedom in a minute, but the important thing is that this t-distribution depends on sample size. So unlike the standard normal distribution where there's just one of them, there's a different distribution for different sample sizes. That distribution is still symmetric and centered around 0 and bell-shaped, so it looks similar, but the difference is that the tails are a little bit wider in the t-distribution, and the fewer samples, and as a result fewer degrees of freedom, the wider that distribution is. And as sample size gets very large, it becomes more and more similar to the standard normal distribution with standard deviation 1. So I thought it would just be useful here to show you how it differs from the normal distribution by looking at the table from your textbook. Let's look at the two-tailed distribution with the probability of 0.05 in the tails. So it's showing you for two tails, it's the probability, it's where you have a total area or probability of 0.05 distributed between those two tails. So degrees of freedom, this is just your sample size minus 1 for the one sample test. For 1 degree of freedom, it's actually 12.7. Whereas, oops, let's see, it's this one that we want to look at. I'm going to circle it. And over here, it's this one. So for infinite, let's start from this end. For infinite degrees of freedom, or n equals degrees of freedom of 500, it's 1.96, a number that you know. So your width of the interval that contains 95% of your probability is plus or minus 1.96 on the unit of t for very large sample size. But as you get down even to 30 degrees of freedom, or 29 degrees of freedom, that would be a sample size of 30, it's 2.05. So that was why I said greater than 300 to actually, to still use a normal distribution when you are estimating standard deviation from a sample. Because even at n equals 30, we've gone from 1.96 up to 2.05. It's not a trivial difference. So just a little bit more on this idea of the degrees of freedom. It's something that you'll calculate in a number of different situations. For the one sample test, it's easy. It's your sample size minus 1. But more generally, it's the number of independent observations that you need to calculate that statistic, or that you did use to calculate the statistic, minus the number of parameters that are estimated in the meantime. So in this case, we estimate the mean x bar, and that's the only thing and that takes away 1 degree of freedom. Alternatively, and maybe an easier way to think about it in most cases, it's if you know the value of the statistic, it's how many observations you could take away and recover them from having that value. And in this case, you could take away one of your data points, and if you knew the t statistic, you could calculate what that data point was again. So if you have a normally distributed population, we're still making that assumption, but you're estimating the standard deviation from the sample, then you're going to use the t distribution for constructing your confidence interval, and you'll use it for more things in future classes. And instead of using the plus or minus z alpha over 2 or 1.96 for the 95% interval, you'll use this t alpha over 2. Alpha being given by this equation, it's 1 minus the percent of your confidence interval. So for a 95% confidence interval, it's 1 minus 0.05 times 100. So the 95% confidence interval alpha is 0.05. For the 99% confidence interval, alpha is 0.01. So you would take that alpha, 0.05, 0.01, divide it by 2, and your degrees of freedom, and you would look up the value of t that you use instead of looking up something on your z table. And it's just a little bit more complicated because instead of before you like looked up your Z statistic, there was just one of them. So you would get like rows, you know, to get your first decimal place, and then columns to get your second decimal place. With the t-table, you only have one column for each specified probability value. So it's not nearly as fine-grained as what you had for the standard normal distribution. But you can, for important values like alpha over 2 equals 0.025, you can look up the value for your given degrees of freedom. And you're going to get some practice doing this. I also put a link to a video that can walk you through it step by step using your table. So here's an example of using it. Suppose we've got a small batch of beer with just, or we've got 5 homebrewed batches of beer. We take a sample from each of them and we calculate their alcohol contents. Then we want to construct a 95% confidence interval for the average alcohol content that the procedures we are using are going to give. And then the related hypothesis test, which we're not really getting into until next class, would be, is there evidence against some particular null hypothesis, such as the average alcohol content being 5%? So if we were going to do this, and I guess we're a little bit short on time to actually go through it, first step would be to calculate the mean of these 5 values, calculate the standard deviation of those 5 values. From the standard deviation, we calculate the standard error, which is going to be standard deviation over square root of 5. What's going to be the degrees of freedom? 4. Yep. So at a 95% confidence interval, we would go back to this table, look under the two tails 0.05. So for 4 degrees of freedom, T is 2.78. We're going to use this 2.78. And then we're going to use this formula for the confidence interval, with T equal to 2.78. 2.78. So it'll be the mean of those 5 values plus or minus 2.78 times the standard deviation over square root of 5. Is that okay? It's pretty mechanical. Once you do it a few times, it'll be fine. And this to test this null hypothesis, in this case, all we would have to do is see whether that 95% confidence interval includes the value of 5. Mm-hmm.
Are there any like
So we're not going to use one-tailed too much. It's sort of, there are not many situations where you want to do a one-tailed test. But no, you would use the same distribution. It's just you would calculate the area under only one tail. So if you were doing a one-tailed hypothesis test at an alpha of 0.05, instead of using this 2.78, you would use this one that is 2.13. Right, you're going to use alpha instead of alpha over 2. So, yeah, because you can imagine if this area here contains 0.05 of your probability, then if you want the value that contains 0.05 under both tails, it's going to be something a little bit further out like that. Yeah, I don't like getting too much into one-tailed tests because they can get confusing in that the direction matters as well. Like it matters whether your observed value is above or below, and what your one-sided hypothesis test was. And they're more easily questioned than a two-tailed test. They're less conservative. So just to summarize the assumptions, we still have to assume data come from a statistically random sample from a population that is normally distributed, unless we have some very large sample size. These procedures are what we call robust, in that the outcome is not too sensitive to the assumptions made. And particularly, it's not too sensitive to this assumption of a normally distributed population. So it's not too sensitive, and additionally, it tends to be conservative in that if that assumption is violated, it will tend to result in us giving a confidence interval that is too large, or a p-value that is too large. It won't tend to make you too sure of your results. You'll be not sure enough of them. With the exception that one-sided tests tend not to work well if the assumption of normality is violated. Here are just some sort of rule of thumb practical guidelines. If you have a sample size of less than 15, use the T procedures if your data are close to normal. Otherwise, you'll need what we call a non-parametric alternative. If sample size is more than 15 but less than 30, then you can use the T procedure unless there are major outliers or skewness. And if you have a large sample size greater than 30 or 40, then you can use the T distribution anyways, even in the presence of outliers and skew. But that assumption of the statistically random sample is always important. If that doesn't hold, then all bets are off. All right, one more Q&A before I let you go. When estimating standard deviation from the sample, instead of knowing it from the population, you use the T distribution. Yep, true, yep, that's when we use it. Is the 95% confidence interval going to be larger or smaller when using the T distribution rather than when using Z? Larger, that's right. Yeah, the tails are fatter on the T distribution. And as n increases, the T-based confidence interval becomes more similar to the Z-based confidence interval. True. Good. Just to wrap up, so the confidence interval it's an interval that is likely to contain the true population mean, and it represents our uncertainty due to sampling variation. If you want a high confidence, then you need a large margin of error to be more sure that you don't make a mistake, that margin of error really does contain the true population mean. Your best estimate from the sample is at the middle of your confidence interval. The standard error and the confidence interval have to do with properties of the sampling distribution, so they don't tell you anything about variability in the population. They tell you about variability of the averages of samples. And when we have small samples and we're estimating the standard deviation from the sample, use the t-distribution. And that's all for today. So I'm going to have to go do a peer observation of one of my peers here, and then I'll try to join you a little bit later in the lab. Not sure exactly when I'll be able to get there, though.